Okay. Section 5.5 is alternating series. Okay, so the comparison test and the limit comparison test had only worked when you had, positive terms being added. The alternating series allows us what happens when we're adding a positive and a negative. Okay, so okay, so let's get into alternating series. Okay, we're going to use something called the alternating series test. Okay, and this says that if we have a series that alternates, n equals 1 to infinity, of negative 1 to the n minus 1, okay, or n plus 1, it really doesn't matter. Okay, the minus 1 or plus 1, that just allows me to start off with a positive constant first. Okay, positive coefficient first. And this is b sub n is some series. Okay, that equals b1 minus b2 plus b3 minus b4 plus dot dot dot. Okay, so it alternates in this pattern: positive, negative, positive, negative. Okay, if this series satisfies the following two conditions, okay, then the series is convergent. Okay, the first condition is that the terms have to be decreasing. Okay, or b sub n plus 1 is less than or equal to b sub n for all n. Okay, it must be decreasing. And the second thing that it satisfies is that the limit as n goes to infinity of b sub n must equal 0. The terms must be going to 0. Okay, so if the terms are constantly decreasing and they're going to 0, then the series diverges. I'm sorry, converges. Okay, and this is called the alternating series test. Okay, so let's look at an alternating series. I want to know, is the following series, okay, is the following series convergent? Negative 1 to the n minus 1 of 1 over n. Okay, is this guy convergent? So if we look at a few terms here, if we say n equals 1 to infinity of negative 1 to the n minus 1, 1 over n, that's going to be equal to negative 1 to the 0, 1 over 1, okay, plus negative 1 to the first, 1 over 2, plus negative 1 to the second, 1 over 3, plus dot dot dot. Now the even powers, they're all going to be positive powers of positive values of negative 1. Okay, so this is just going to become 1. All the odd powers are going to go to negative, so it would be 1 minus 1 half plus 1/3. The next one would go to, maybe I'll write the next term here, negative 1 to the third, and then 1 over 4. So that's an odd power, so that's going to go to a negative. Okay, and so this thing alternates. And what this really is this is the alternating harmonic series. This one alternates though. Okay, so we're not adding all of the terms. We're actually taking a value and then subtracting, and then adding a little bit more back, and then subtracting off a little bit more, and then it keeps going. Now this one actually does converge, and what's happening? Okay, if we look at the sum of these, okay, we start off at 1, and then we immediately cut that in half and go to 1/2. And then we add back a 1/3, and then we cut it down again and do 1/4. And so this thing will continue to oscillate back and forth. Okay, the partial sums, the S of n's, will oscillate back and forth, but they're going to get smaller and smaller and smaller, and they're eventually going to converge to some value. Okay, now we can prove this using the alternating series test. Okay, let's look at those two conditions. B sub n is 1 over n, and we want to know, is 1 over n plus 1 always less than or equal to 1 over n? And that is true. And we also want to know, is the limit as n goes to infinity of 1 over n equal to 0? And that is true. Therefore, by the alternating series test, okay, the summation n equals 1 to infinity of -1 to the n minus 1 of 1 over n is convergent. So we saw that the harmonic series is divergent, but the alternating harmonic series is actually convergent. So kind of an interesting result. Okay, let's do another one. Is the sum n equals 1 to infinity of -1 to the n plus 1 this time of n squared over n cubed plus 1, is this convergent? Can I prove that this is convergent? Okay, so let's look at the criteria for this thing alternates, obviously. If we wrote out a few terms, you would see that this is going to be -1 to the second power times 1 squared over 1 cubed plus 1. Okay, plus this is going to be -1 to the third power. And this is going to be 2 squared over 2 cubed plus 1 plus, and this is going to go like that forever. This becomes 1 times 1 over 2. This is -1 times 4 over 9. Okay, and this would become 1/2 minus 4/9, and then it would alternate. If we looked at the next term, this is -1 to the fourth, 3 squared over 3 cubed plus 1. This would be 9 over 28. Okay, plus this would be a 1, 9 over 28. So this is 9 over 28, but then the next one would be subtraction. Okay, which it does alternate. Okay, so let's see, does it satisfy the criteria for the alternating series test? So we want to know, does Bn plus 1, does the next term, is that always less than or equal to the previous term? Okay, so if I plug in n plus 1 here for n, over n plus 1 cubed plus 1, is that always less than or equal to? Okay, n squared over n cubed plus 1. Okay. So this becomes n plus 1 squared time, if I cross multiply, n cubed plus 1. Okay, is that less than or equal to? n squared times n plus 1 cubed plus 1. Okay, so let me multiply this out. This is n squared plus 2n plus 1 times n cubed plus 1. Is that less than or equal to n squared times n plus 1 cubed? That's n cubed plus 3n squared plus 3n plus 1, using my Pascal's triangle on that. Okay, let's add a 1. Let's distribute this out. I would get n to the 5th plus 2n to the 4th plus n cubed plus n squared plus 2n plus 1. Is that less than or equal to n to the 5th plus 3n to the 4th plus 3n to the 3rd plus n squared plus n squared, which is 2n squared. I'll just write that as 2n squared. Okay, and now what I want to do is I want to get rid of kind of what they have in common here. Okay, is if I subtract off n to the 5th, and I subtract off, say, a 2n to the 4th, and a minus n cubed, and a minus n squared, so minus 2n to the 4th, minus n cubed, minus n squared, I get 2n plus 1 is less than or equal to n to the 4th plus 2n cubed plus n squared. And is that true if n is positive? Well, here I have 3 terms, and here I have 2 terms. Okay, so let's say that n was equal to 1. I would get 2 times 1 plus 1, that's 3, is equal to, 3, which is less than 4. Okay, if I plug in 1, if n is equal to 2, okay, we're going to get 2 times 2 is 4, plus this is 5, which is less than a huge number here. This is 16 plus 16, which is 32, plus 4, which is 36. And we can see that, yes, these numbers are going to be bigger. They're going to dwarf these numbers eventually, and these are going to be the smaller. So it does check. Okay. Now let's do the limit. That was the kind of the hardest part of this problem was that one. Let's do the limit as n goes to infinity of bn. We saw that that was n squared over n cubed plus 1. Let's use L'Hopital's rule on this. Okay, derivative of the top is 2n, derivative of the bottom is 3n squared. Okay, this equals the limit as n goes to infinity. Let's cancel out the n here. 2 over 3n, and that does go to 0, so that checks. So therefore, by the alternating series test, just call that AST, this series is convergent. Okay. Okay, let's try one more of these. Okay, number 3. Is the series summation n equals 1 to infinity of negative 1 to the nth power I'll do n minus 1. Okay, of 3n over 4n minus 1, is this thing convergent? Okay, now we can kind of go through the long process of doing this or the short process. Okay, we know that we need two criteria, right? Okay, we need to know that these terms are always smaller. I would need to know that bn plus 1 is less than or equal to bn is 3 times n plus 1 over 4 times n plus 1 minus 1. Is that always smaller than the previous term, 3n over 4n minus 1. Again, we could do the cross multiplying thing here. Okay, and we could prove that, yes, that is true. This actually checks. Okay, but we can save ourselves some algebra here by just jumping to number 2. Does the limit of b sub n, 3n over 4n minus 1, does that go to 0? And again, if we use L'Hopital's rule, we get the limit as n goes to infinity of 3 over 4, which equals 3/4, which does not equal 0. So this does not converge. So this diverges. So the series diverges by the alternating series test. Okay. Because what eventually this thing does is it oscillates. We get a value. We start with a value, and then eventually we end up adding 3/4 and then taking that 3/4 away, and then adding the 3/4 and then taking the 3/4 away, and then adding 3/4 and taking the 3/4 away. And as this thing tends to infinity, we keep adding and subtracting the same number, and this just basically bounces back and forth and oscillates back and forth between two values, and it never converges to a single value. Okay, so this thing actually diverges. Okay. Let's talk about the alternating series estimation theorem. Okay, if S equals the sum of negative 1 to the n minus 1 b sub n, okay, where n equals 1 to infinity, okay, where, so that's the sum of this series, where b sub n is greater than 0, b sub n plus 1 is less than or equal to b sub n, and the limit of b sub n is equal to 0 as n goes to infinity. So we know it's a convergent series, okay, thus convergent. Okay, we know it's a convergent series, and it's going to converge to some value s. Okay, if this is true, then the remainder of r sub n is equal to the absolute value of s minus s sub n, which is less than or equal to b sub n plus 1, the nth plus 1th term. Okay, so that remainder is less than, okay, or what we would call the error, okay, is less than the n plus 1th term. The nth error is less than the n plus 1th term. Okay. So let's see how this works in practice. Find the sum of the series summation n equals 1 to infinity of -1 to the n minus 1 all over n factorial, correct to 3 decimal places. Okay. So n equals 1 to infinity, okay, of -1 to the n minus 1, okay, all over n factorial. Okay, so is this thing going to converge? Let's just test that. Let's just make sure that the alternating series test works. Okay, let me write it like this, 1 over n factorial. Is 1 over n factorial, is that greater than 0? Yes. Is 1 over n plus 1 factorial always less than 1 over n factorial? Yes. Is the limit as n goes to infinity of 1 over n factorial equal to 0? Yes, all of those work, therefore it converges. Okay, by the alternating series test. Okay, so we're good there. Okay, we want to know, okay, then how do we get 3 decimal place accuracy? That's 0.001 accuracy. Okay, well, what I can do is I can just look at the terms, and when I get to terms that don't fluctuate within 3 decimal places, then I can stop and back out, and then I can say, well, the nth partial sum, S sub n, okay, the error on S sub n should be less than Bn plus 1. The nth plus 1 term should give me an error less than S sub n, than the nth partial sum. So let's see how this works. So B1 here, if I were to go B1, that's going to be 1 over 1 factorial, which is equal to 1. B2 is 1 over 2 factorial, which is 1/2, okay, or 0.5. B3 is going to be 1 over 3 factorial, which is 1 over 6, which is approximately 0.16 forever. B4 is equal to 1 over 4 factorial, which is 1 over 24, which is equal to 0.0416 forever. Okay, we still get a lot of fluctuation, so we're trying to get something that doesn't have a lot of fluctuation. Let's keep going. Okay, B5 is 1 over 5 factorial. That's 1 over, remember, factorial is all those numbers. So like 5 factorial is 5 times 4 times 3 times 2 times 1. So I'm really just multiplying by the next number from the previous factorial. So 24 times 5 is 120. 1 over 120 is 0.0083. So we're not adding on that much. We've got maybe 2 decimal place accuracy here because we've hit double zeros. Okay, let's try to get triple zeros. So B sub 6 is 1 over 6 factorial, which is equal to 1 over 720, which is equal to 0.00138 repeated. And then B7 is 1 over 7 factorial, which is 1 over 5040, which is 0.000198. Okay, and here we have 3 decimal place accuracy. So we're not going to be, if we continue on, we're not going to be adding or subtracting anything more or less accurate, okay, that's going to affect my sum. Remember, we're summing all these up. We're adding all these values up to get our partial sums. And so we're not going to be adding anything that's going to change my accuracy from here on out. So we can say that S sub 6 is within, because it's always one less, okay, S sub 6 is within 3 decimal place accuracy. And if we were to use our calculator and add all of this up, just the first 6 terms, we would see that S sub 6 is approximately 0.632 rounded, correct to 3 decimals. So we just had to go to the next one and find out where those triple zeros kind of go down and hit the triple zeros and then back one out. And we get S sub 6, okay, is correct to 3 decimals. Okay, because again, the absolute value of S minus S sub n would be less than or equal to Bn plus 1. That's really what we're doing here. Okay, the remainder is less than that, so we only have to go out to n, but we did have to go out to n plus 1, okay, where n plus 1 was 7, so n is 6. Okay, and that is 5.5.